try to finish up section 4.5. We've been looking at the graphs of the sine and the cosine functions, and now we've been looking more recently, we've been looking at the transformations of the graph. We looked at the vertical and the horizontal dilations where we stretch or shrink it. We also looked at translations. Now we have, and also a few reflections. And now we have an example here which kind of involves it all, as you can see here. Now I have given y equals -2 sine of the quantity, the opposite of pi over 6x minus pi over 2, end of quantity, plus 1. I'm not going to leave it in this form. I'm going to rewrite this and factor out the negative pi over 6, so I have it in a form where I can more easily find my translations and my value of b, which affects the period. So by factoring out a negative pi over 6, which I've done down here, skip down to here, you can see that when you factor negative pi over 6 out of negative pi over 6x, it leaves the x, and when you factor negative pi over 6 out of minus pi over 2, you're dividing by negative pi over 6, and that is going to give you a plus 3. If you can see that, negative pi over 2 divided by negative pi over 6 is negative pi over 2 times the reciprocal, which would be negative, let's see, do I have that right? Negative, factoring out with the reciprocal, which is negative 6 over pi, and these are going to cancel. I'm going to end up with a negative over negative, negative 6 over negative 2, or a positive 3. That's where this plus 3 comes into play. If I could do arithmetic, I would have done that a little bit more quickly. But that's this equation transformed so that I can see my value of A, my value of B, my value of H, and my value of K. But I've been mostly working with the values of B that are positive. And this is negative. So that involves some type of reflection. Well, because this is an odd function, sine is an odd function, which means the opposite, f of the opposite of x is equal to the opposite of f of x. If I take the opposite of this, using the fact that it's an odd function, then I get the opposite of the original. And you can see the opposite of negative 2 is going to give me a positive 2. So now, there's my value of A, there's my value of B, there's my value of H, and there's my value of K. I'm asked in part A to identify the amplitude, the period, the phase shift, and the vertical shift. Well, the amplitude is easy enough because it's the absolute value of 2, which is 2. The period, a little bit trickier, is the period of the parent function, 2 pi, divided by b, which is, in this case, the absolute value of b, but in this case it's positive, pi over 6, which is 2 pi over 1 times 6 over pi, which is 12. So that would be the period there. The phase shift is the h, which is a negative 3, because it's in the form x minus h. So what I usually do for the phase shift, instead of saying necessarily negative 3, a lot of times I'll say 3 to the left. And my k is a positive 1, so my vertical shift here would be up 1 upward. And that's what I'm going to use to help me with the sketch, because I know what the sine wave looks like, but with all these transformations I have to be very careful. Now, before I graph this entire function here, I'm going to simplify it a little bit. I'm only going to graph 2 sine of pi over 6x. I'm not going to do the transformations, the translations I should say. I'm going to do those at the end. So I'm going to pick some key values. Now remember, whatever I plug in for x, I'm going to multiply it by pi over 6. These are the angles I want to use here in the middle row. So if I take each one of these angles in the middle row and I divide them by pi over 6, I get these values, because these are the ones that I want to plug in and get equal to this. So 0, 3, 6, 9, 12, that is going to be one complete and full period. So I plug these values in. Let's say I plug 0 in. Pi over 6 times 0 is 0. The sine of 0 is 0 times 2 is 0. You can see the y value right here. Oops, I have one missing. If I plug 3 in, pi over 6 times 3 is pi over 2. The sine of pi over 2 is 1 times 2 is 2. If I plug 6 in, 6 times the pi over 6 is pi, sine of pi is 0, times 2 is 0, and all the way through. So these are the points that I'm going to graph. I'm going to do this in, I've got this purple color pen here. I'm going to graph 0, 0. I'm going to graph 3, 2, 3, 2, about here. I'm going to, it's important to use graph paper, people. I'm going to graph 6, 0. I'm going to graph 9, negative 2. I'm going to graph 12, 0. And you can see here that those points would be enough to come up with a graph. That's supposed to kind of be a curve there. Not very curved, is it? A little bit better. And this would continue. I mean, that's only one full period here, but this would continue. And I'll just go ahead and kind of represent that with some dotted, with a dotted curve here. It would continue like this. And over here, it would continue like this. And you can see that this would go on forever and ever and ever, because the domain is the set of all real numbers. Now, I'm not done. That's this guy right here. But I'm wanting to graph this guy. So, I grab a different color pen. Let's see, I have a green one somewhere. I'll use this one. It's not the one I wanted, but it's okay. It'll work. And I'm going to make a translation of 3 units to the left, 1 unit upward. So I'm going to start with the 5 key points that I have here, 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 and here. And I'm going to move them 3 to the left and then up 1. So I'll start here with the point at 0, 0. 3 to the left, up 1. Then I'll start with, I'll go to this point, which is 3, 2. So that'd be 3 to the left, up 1. Let's see, 3, yep. And then I go 3, here at 6, 0, 3 to the left, up 1. This point way down here, 3 to the left, up 1. And then this point right here, 3 to the left, up 1. And I hope that you can see that the solid purple curve is now been translated to this green curve here. And then this pattern can continue if I keep on going. Like, for example, this point here, 3 to the left, up 1. 3 to the left, up 1. And you can see that my graph would continue. If it only asked for 1 full period, then this would have been enough. But I could have continued this. Let's see, 3 to the left, where I'm at, 15, up 1. 3 to the left, up 1. And I would have continued and so on. Maybe not quite so much there. So that's the graph of this guy. I can't do this myself. I have a lot of trouble trying to do this all at one time. But if I take care of the dilations first, picking very special values for x, key values for those key points, then I can make the translations at the end a lot easier and adjust it from the purple to the green here. Now, if you're doing this problem for an assignment and you want to make sure that I grade the right stuff here, then you either have to label which one is which. Like in this case, I kind of color-coded it, because the one in green here is the one that I'm trying to graph, or erase the old graph there that's in purple, and then that way it leaves only the final result. Now, that's a lot of stuff. That's why this has been spread out over so many videos. But that should give you a pretty good idea of how to go about and graph these various sine and cosine curves. Now in the next section, we're going to graph tangent and cotangent, secant and cosecant, and we'll look at transformations there as well. But we're starting out with the sine and cosine, give you a good idea of what's going on with them and some of the subtleties. Now, what would be really sneaky would be, given a graph that looks like a sine or a cosine wave, like the one here in green, could I write the equation? Or if I was given information, could I write the equation? Well, graphs that have this appearance of a sine or a cosine graph are called sinusoidal. Okay? And we can take graphs, or we can take information about the graphs, and we can write an equation that it models. And there are all sorts of applications here. I mean, think about things that are periodic. The level of the tide. You know, high tide, low tide, high tide, low tide. The cycle of the moon, full moon to no moon to half moon and so on down the way. Sound waves. If you've ever seen one of those, I think they're called like an oscilloscope, you get that sine wave kind of a deal with the sound and such. At least on all these scientific movies that I've seen, they have that. Especially the ones from the 50s, where they have that in the lab to create the Frankenstein monster or something. A mechanical metronome. Now, I took piano lessons when I was a kid, but I didn't have one of the metronomes. And I always see them in the old movies. Watched way too many movies. I always see them in the old movies where they have it sitting on top of a piano to help the student keep time as they're practicing. There's the teacher, there's the child that's taking the lessons, and then at the top there's this, typically it's kind of a triangular looking shape, the ones that I've seen, and they have like an inverted pendulum that goes back and forth and it clicks. And the clicking sound gives the student, the piano student, hopefully the ability to keep time with the music. Well, we have a mechanical metronome. If you don't know by my description, just Google it. It uses an inverted pendulum that makes regular rhythmic clicks as it swings to the left and to the right. With each swing, the pendulum moves 3 inches to the left and 3 inches to the center position. The pendulum is initially pulled to the right, starts off to the right, 3 inches, and then is released. It returns to the starting position in 0.8 seconds. So this information is all important. I don't have a graph. I'm given the information to find things about the period, the amplitude, and so on. Assuming that this pattern continues indefinitely and behaves like a cosine wave, write a function of this form here. Now again, notice how they throw the b in here and didn't factor it out, but that's okay. We know what we're looking at here. This is going to be our, eventually, this constant here, once I factor the b out, that's going to be my phase shift, and this plus d here is going to be my vertical shift. The value of h of x is the horizontal position in inches relative to the center line of the pendulum. Well, it doesn't really sound like there is any type of translation involved, no shifting. So remember, I'm going to rewrite this to put it into this form. Okay? But since there's no shifting, we're going to say C and D from here, or H and K from here, are both 0, and that gets us to this. Remember, x of t is the horizontal position. Now, we know the amplitude is 3, because from the center it goes 3 to the right, then it goes 3 to the left. So because of that, A is 3, and I'm going to plug a 3 right in there. And since the period, it goes back to its starting position in 8 seconds for time here, that's why we have a t here for time. We take the period of cosine divided by whatever b is going to be to give us 0.8. Well, if I solve for b, I get 5 pi over 2, so that goes right in here. And this would be the equation that models this particular application. Now, there'll be problems that involve the level of tide, high tide, low tide. You can get the amplitude and such, all sorts of different possibilities. So be sure to give these problems a try, and remember always, practice, practice, practice.